Lesson 99, using vectors. A vector is a quantity that has magnitude, orientation, and direction. Oh yeah. Well, we're going to add orientation in there.
No.
So we can express a vector using Cartesian or complex coordinate systems. So here's an example of vector z. Here's theta, the terminal point, xy. So your Cartesian matrix is x over y, so whatever x is over y. If you wanted the complex, is just x plus y times I. The magnitude looks like you're saying the absolute value of vector z. It looks like that, but it means magnitude. And that is equal to the square root of x squared plus y squared. Theta represents your orientation. And if you remember, theta equals tangent inverse of y divided by x. So let's give you an example. So here's our example. We have terminal point 8, 2. We can do our Cartesian matrix. It's just x over y, so it's 8 over 2. The complex number is 8 plus 2i. The theta is tangent inverse of 2/8, which is approximately 14.04 degrees. And if we wanted to find the magnitude, it would be the square root of 8 squared plus 2 squared. Square root of 68. Just a minute. Which is 4 root 7, maybe? No, 2 root 7? Let me see. Oh no, 2 root 17. There we go. Okay, now a dot product is a scalar quantity. Scalar just means like a number. It's not a vector. So if vector A ends at 2, 9 and vector B is at 6, 3, we want to do the dot product. It looks like this. We do A vector A dot, which is the product vector B. And we write it like this. We do 2 6, 3. And that equals 12 plus 27, which equals 39. So the dot product of these two vectors would be 39. If I call this x sub 1, y sub 1, and this x sub 2, y sub 2, I can, there's an equation we can use. It can be found by using the magnitudes and the angle between the vectors. So we found it this way, which I think is a lot easier. But you can, we're going to do the angle measure between two vectors. So to find the angle measure between two vectors, you can find the value of theta by setting the equations equal to each other and solving for theta. Okay, so we take the magnitude of the vector times the magnitude of the other vector times the cosine of theta. That actually equals the dot product. So it equals x sub 1 times x sub 2 plus y sub 1 times y sub 2. Now the magnitude is just the square root of x squared plus y squared. And then you solve for theta by dividing by these square roots and then taking cos inverse. So theta equals the cos inverse of this dot product x sub 1 times x sub 2 plus y sub 1 times y sub 2 divided by the product of their magnitudes. Oops, this should be 1, 1. You got it. Did it just click? Oh, okay.
I realized why you usually mix up your children. It's because you've got all this math crap in your head.
Yep, I mix
And that's
up.
why you think your children are you.
That's, yep.
See, the math crap is just crowding out your brain. It's not letting anything else in.
Yep,
And
yep.
so-
And a lot of things fall out, like dates and names. It's the truth, though.
She won't remember you told her that.
It's true.
She knows it's true, so
It will be gone.
that's why we understand each other. That's why people think she's rude, but she's not trying to be rude.
I'm not
She's
trying
just
to be
blunt.
rude. It's just, yeah. Okay, I am turning the page
But don't turn it yet.
because if you know the magnitude and the orientation of a vector, you can derive the horizontal and vertical components by using the properties of a right triangle. So let me show you what that means. I might have to draw you a picture though. Okay, I'm turning the page. Okay, we're going to use vector A. So just draw a generic vector A and theta, and then call this line right here will be y, and of course this one's x. So if I wanted to find the cosine of theta, I do the adjacent over the length of the hypotenuse, which is the magnitude of the vector. So if I wanted to solve for x, I would say that x equals the magnitude times the cosine of theta. We already knew that though, I'm pretty sure. The sine of theta equals y over the magnitude of vector A. So y equals the magnitude times sine theta. Maybe we didn't know that. We knew that in geometry anyway. Okay, that's all we're going to go over today.